All right, ladies and gentlemen, it's a pleasure to have all of you back here once again to enjoy the journey of the shadows of multivariate data analysis. It's been a real joy. The world is suffering from COVID, and we thank God we are still alive and kicking and acquiring knowledge to the superlative degree. So once again, you're all welcome. The last time we ended at factor analysis, we know the theory, but what we are going to do today is a practical demonstration of factor analysis. And we are going to continue using the same data set that we did before, because factor analysis is a build-up of principal component analysis. And you're going to see that pretty soon here. So let's begin. The first thing you want to take note is that in R, there's a function we use for factor analysis. There are actually two functions. One is known as factana. It uses maximum likelihood method to find the loadings. And the idea is that the number of factors that are needed to be extracted must be specified ahead of time. Now, you might know that in PCA, you did not know the factors to be specified. So you use some heuristics. You remember, you use some heuristics to be able to arrive. You use the elbow effect. You use the eigenvalues. You use the standard deviation. You use the biplot, the scree plot, and all of those things to come out with how many factors now, or how many components to select. Now, the factor analysis assumes that you already have the number in mind, okay? And so what you do is that you use that prior knowledge to be able to execute everything. So what we are going to do is that we are going to use the function FA, which is included in the psych package. Now that means that if you don't have psych package, you should install the psych package. I think we did have it, but if you don't, let me show you whether or how you can get it. So if you can see my interface for the R Studio, okay, we are going to do factor analysis. So under number 13, I leave a line under number 13. I'm going to bring a couple of hash signs and write factor analysis. Okay. Factor analysis, just to indicate that we are going to do factor analysis. Enter and go to the next page. Now, under command number 14, okay, what I'm going to do is that I'm going to, first of all, look on the right under packages. On the right under packages, you look for packages, you click install, and then you start typing psych, okay, PSY psych. You see that showing, and then you install that psych into the library if you don't have it. Now, how do you know whether you have it? You can go to the search of the packages here. Okay, under search. And then you start typing. You start typing PSY, and it's there in my case. So if it is there, you just take it. Okay, and the command will show itself. The command you are supposed to type will show down here, library psych. So let's just take it there. The only reason why it is showing there is because I clicked it. Other than that, you type library psych and run it. Okay, run it. And when you run it, then you see it down there in the console. So for those of you who can do that, please type library psych. That's the first thing you want to do. Okay. Now, let me take you back to the instructions we were having. And so the function is library psych. The package is library psych. We've invoked that package. Now the FM, we're going to see the function I'm going to use. Okay, you're going to see down here. And inside that function, there's something you will specify called FM. It is an option that will specify the method of estimation. And I just told you that we have methods like minimum residual approach, You can have ML, which is maximum likelihood estimation. That is how you estimate the factor loadings. You can have another thing called principal axis method. All of these are several methods you can use. Okay, we'll use the common one, the default one. And then the number of extracted factors must be specified by n factors. This is an option you can select. I'm not going to be dealing with so much nitty-gritties of all of these options because we are not going deeper. Okay, there are various rotation methods you can specify under rotate. Okay, you can choose none. The default is the Varimax rotation. We have the Cortimax rotation. We have the Bent-Lati rotation, Geoment rotation, Oblement, Simplemax, Bent-Lati, Geoment, and Cluster. All of them are possible rotation. Now, this rotation, again, is even a little bit complex for some people to understand. It is how you want the factors you rotate at what degrees and how one particular factor will load onto one particular variable. Okay, so we are going to proceed as if we are done with principal component. And in fact, if I'm doing an exam situation, I will give you the story as if you have already done principal component. And now you have the number of factors. And now you're going to use the number of factors. So based on the summary of the principal component analysis, it appears last week that we had two principal components. Okay, so if you can remember, we retained two factors, okay, because they have eigenvalues which were greater than 1. So that was a previous situation. And it was confirmed using the standard deviation, the scree plot, and several other factors. So we can assume that probably two factors are extractable and now can do our factor analysis. Practically, we can now do our factor analysis. How do you proceed? Well, first thing to remember is that the data is already loaded in R in our case. So we want to go to our data and type this command to see the head of the data. Because the thing is that you want to be sure that the data is there. Do you remember that the name of the data we gave was EG? Okay, EG. Now, if your data is not there, okay, and I'm going to show you some few things. If your data is not there, and I'm going to show you the R. Oops. I'm going to show you the Excel of the data. Ladies and gentlemen, on your screen in this Excel was the data. Okay. So if your data is not there, you have to Control, highlight, Control A, and then Control C to copy the data again into R. Okay. And that is because we did not attach the data into the full memory of R. So we got to load it again. So I now go to my R Studio. If you have a question, always let me know. And then the command we used the last time was eg read.lm. So I just want to load that data. Okay. I have uploaded the data because I ran that command. Then let me just highlight the eg. And then down there, you can now see the data. Okay, you can now see the data showing down there in the console. Okay, down there in the console. And then we did every possible thing. Now, to see the head of the data, you just type head into bracket EG. It will just show you the top 6 observations. That is if the data is usually small. Okay, it will show you the top 6. Oh, sorry, somebody said you can't see my R screen. Are you sure? Because it tells me that you are looking at my I screen. Please, can you see my R screen? If you can see, type yes. Okay, majority of your colleagues are saying yes. So please give yourself time, it will show. All right. So now that you can see, we are going to now, we have just looked at the head of the data set. Okay. So we are going to type this command, which I know many of you have already done. I brought you back to the slides. We're going to type this command in blue into the R, and then we'll run this command. Okay, so please do that. The command is known as FA after PCA. That's the name I'm calling it. That's the equation I'm giving to it. That is factor analysis after principal component analysis. That is the name I'm giving to it. I'm taking this into R. I'm taking this into R. Okay, or if it were you, in your case, you have to type this into R. Okay, let me go back to R. I'm now going back to R. Oops. So I'm going to type what I want you to type, okay? I'm going to type the same thing there. So it is FA after PCA equal to, I'm just writing the factor analysis equation, equal to facternal. Facternal, that is what has come. And then the name of the data set that we gave was EG. You bring a comma. And then the next thing is factors. Then you do equal to. This is where you write how many factors you selected from the PCA. And guys, do you remember how many factors we selected from the PCA? Let me know. I want to be sure you are aware. So you do that. Let me see what factors some of you have written. How many factors did you have from the PCA? We had 2. Very good. So you type factors equal to 2, comma, then you do rotation. Rotation. Okay, the rotation, I told you we will use a default, and the default is Variance. Okay, so you bring your double apostrophe and type Variance rotation. This is the default. Now, if you are wondering about lots of things about rotation, I can give you one, but like I said, the Variance rotation, then you do a comma and then type scores. Okay, so these are factor scores. And under scores, you select regression. Regression. And then you put that regression in. Double apostrophe. Fantastic. So once you've done this, you've been able to execute your factor analysis command. It's like a regression result. Okay. So we are going to execute this. Control Enter, or while the cursor is blinking in that section, you click Run. Look down there, it's showing blue, which means that everything has been beautifully loaded. Okay. Everything has been beautifully loaded. What's next? How do you know that the results is there? Well, it's a very simple thing. The next thing to do to be sure that the result is showing is just go and run the FA after PCA. So you highlight this FA after PCA, and then you run that alone. Now look down there, your entire results will be showing. Okay, I want you to take your time and feel and enjoy the results that we have been looking for since 1912. Okay, this result is what, if it is an exam, I would have given you. And then I'll ask you multiple questions about this result. Okay, so we are going to do a similar questions about this result. Now, there's something you will notice about this result, which is different from the principal component analysis results. And one of the key things is at the last sentence, the p-value is. The p-value is. And you remember we said that the factor analysis is an equation. And we even had a fundamental theorem of factor analysis, you remember? And so anytime it is an equation, it's called kind of an equation, there must be a p-value, a statistic, a chi-square statistic, and a p-value. Okay, so I'm going to ask some questions related to this, and then we will answer. So this result must be in front of you. Every question I ask you, okay, you want to put the question down. You want to put the question down, okay? So the first thing we want to talk about, and I want to take you back to the slides just to help you to appreciate what we are doing. The first thing we want to talk about is known as uniqueness. Uniqueness. What is uniqueness? What is uniqueness? What is uniqueness? Now, we said it the last time. Uniqueness comes from the word something you have in common, something you have that others do not have. Okay, so uniqueness, every variable, like variable 1, variable 2, variable 3, every one of the variable has a uniqueness value. Every one of them has a uniqueness value. Okay. And it is that percentage of the variable that, so when you take a variable like variable 1, that portion, that percentage of that variable that cannot be predicted from the other variables. In other words, it is latent. Okay, so it is like part of that variable which is latent and therefore cannot be explained by the extracted factors. You remember the extracted factors are how many? 2. Okay, let me take you back to the arrow. The extracted factors are 2. So you can see from here that you have factor 1 and factor 2. Okay. Now, each variable has got a portion that cannot be explained by the extracted factors. Whether it's from factor 1 or factor 2, there is something unique about a variable that cannot be extracted, that cannot be explained. So take, for example, variable 1 under uniqueness. If you look at the value, correct to 2 decimal place, how many percent, and please listen carefully, how many percent of variable 1 cannot be explained by the extracted factor? How many percent of variable 1 cannot be explained by the extracted factors? How many? What will you write? What will you write? Okay, that's what we are looking at. What will you write? Think about that very seriously. Okay. Think about that very, very seriously. So we'll come back to it. We'll come back to it, but think about that. Okay. Now let me take you back to the R, to the slides. Okay. In the slide, you will notice the fundamental theorem of factor analysis model. We spoke about this the last time. We spoke about it the last time. The fundamental theorem of factor analysis model. And those are the items in there. We indicated that the intercept is not that much important. Okay, that's what we said. And then we spoke about the common factors, and then we spoke about the latent, the communalities. Okay, the communality, the unique factor. That's the delta I. Okay. The unique factor, the uniqueness. So what we are going to do is that, what was that uniqueness? We said that the uniqueness was a portion or the variability of the information that this variable has, but it's not shared with other variables. Okay. I've already told you last week that try and learn how to write the factor analysis model and interpret the model very well. So you all are good at that. So master that. Okay. So I want you to look at the results now, and I'm going to ask you a question. Okay. Every time you can speak about uniqueness, its opposite is communality. Uniqueness is that portion that is not common to others, which that variable has. But communality is the percentage of the variability that is predicted by the model, or that variance that is shared, or the portion of the variable that is not shared with other variables. That is communality. So there is a connection between communality and uniqueness. One minus the other equals the other. Okay. So for example, communality is 1 minus uniqueness, and uniqueness is 1 minus the communality. Why? Because if you take away what is unique to you, then what is not unique to you is common to others. Okay. Now that means that communality plus uniqueness equals what? You can tell me. That means that communality plus uniqueness equals what? Try and write some, because it's an indication that you are in a world of intellectual masturbation. Okay, very good. Somebody had a question? Okay, that means that you are in the world of intellectual, gymnastics. So it's very important to appreciate what we are doing. Okay, so communality plus uniqueness equals 1. All right, now this is very important. So when we say a variable is informative, listen carefully. When we say a variable is informative, then it means that that variable is relevant. If I say that an Xij is very informative, it's relevant. When it's relevant, what it means is that its uniqueness is not high. When it is relevant, okay, it means that that variable gives you enough information. Okay, so it means that it has something it shares more with other variables. It has a very high communality value. And if you have a very high communality value, it means that your uniqueness is not high, your uniqueness is low. Okay, so intuitively, variables with high communality will share more with other variables. They will have something in common they will share with other variables. Such variables, we say they have high communality, or they are relevant, or they are informative. Take note. Informative, relevant, high communality. Okay. Not informative, not relevant. Okay, then it means high uniqueness. Okay, so take note. Sometimes it can be a little bit confusing, but it's okay. Okay, they just understand that when you are informative and relevant, you have high communality. And that is a principle of what. So I want you to look at the data set again. Okay, and I'm going to ask you this question, going to use the R information. So let me just go back. I want you to look at the question again before we go back. Compute the communalities for variables 1, 3, and 6. And determine which one of them is the most informative and why. So compute the communalities. Let's go back to the R. You see, it didn't ask you to find the uniqueness, because the uniqueness has been given. So it's now asking you compute the communalities for variables 1, 3, and 6. Guys, I want you to compute each one of them for me and tell me which one is the most informative and why you say so. If you are done, you can raise your hand, and then you can exercise your intellectual justice to us. What are the communalities for variables 1, 3, and 6? And which one is the most informative and why? Which one is most informative and why? Who is ready? Who is ready to rock and to roll with the great minds of the world? Okay, Bright. Bright is ready to execute his intellectual justice to us. Yes, Bright.
Okay, sir. So with respect to variable 1, the communal value is 0.99. Variable 3, the communal value is 0.92, and then with that of variable 6, the communal value is 0.62. So I believe that variable 6 is more informative because that is more communal compared to the other 2 variables.
Okay, thank you. I want your answers in percentage. I wanted your answers actually in percentage. So I want you to go back and just give me the answers in percent. I want to check something. Yes,
Yes.
go.
So with respect to percentage, variable 1 gives a communal value of 99%. Variable 3 gives a communal value of 92%. And then variable 6 gives a communal value of 62%. 63% actually.
Are you sure?
So I'm sorry, 53%.
You know how many times I asked you, are you sure, before you got the answer correct?
Yes, sir. Um, I think it was a slip of tongue.
All right.
So 53%.
So what is your conclusion? Which one of them is the most informative and why? Okay.
Okay, so the one that is most informative is the one that has the highest communal value.
And that is what?
Variable 1.
Okay. So you now indicate a variable 1 is the one with the highest communality. And it's not just that. Somebody can also say that is the one with the lowest what? Who can tell us? Among the three, is the one with the lowest what? Type it there. Is the one with the lowest what? Exactly. I like the typing for your lowest uniqueness. That's it. Not lowest variable 6. Okay. It is the one with the lowest uniqueness. It's not just the one with the highest. If it has the highest communality, it has the lowest uniqueness. And therefore, that is why it's the most informative or most relevant. Now, let us interpret the communality value for variable 4. How do you interpret that value? Communality value for variable 4. You see, I didn't tell you to calculate it, but the fact that I'm telling you to interpret it means that you have already been told, you are expected to calculate it. Okay, so let's go to the thing. Go to the data set. This is variable 4. Who can interpret its communality value? You can raise your hand and tell us. How do you interpret the communality value for this variable? Variable 4. You don't have to be explicitly exact. You can use your own words to interpret. Okay. So how will you interpret the communality value for variable 4? Okay. First of all, okay, Comfort, you seem to already. Yes, Comfort, tell us.
Variable 4 has 11% communality with the other variables. And yeah, that's all I can say about it.
So I like the confidence in which you spoke, but that is way out of the line. So let's go to Fred. Fred. Yes. Is Fred ready? It looks like Fred is not yet ready.
Yeah.
Oh. Fred started, but I think yeah, Fred.
Hello. Yeah,
Yes.
so the variable 4 share 88.6% of the portion of the variable 4 is shared with the other variable.
That is not correct. I was very explicit about how you should answer these questions. So let's go to Maida. Maida, what will you say? Oh, Maida is gone. No, that wasn't correct. Yes, Maida.
Yes, Doc, please. So 89% of the variation in real.
All right, okay. So I'm sure she's on the right track, to be honest with you. Okay, 89% of the variability is not, I told you to round it. I think, Fred, you missed that point. Okay. So is the 89% that you're going to interpret. All I want you to do is to give me the interpretation. Okay. So you say that 89%, after you calculated the communality, 89% of the variability inside variable 4 is shared with other variables in the factor analysis model. 89%, okay, of the variance or the variability, okay, is shared with other variables in this factor analysis model. That is how you interpret this. Okay. So you now do 100% minus 11%, and then you use that to do the interpretation. Very good. You should be able to learn how to do all of these interpretations. So we've been able to interpret and then do several other things. Now let's go to the next question that will be necessary to try and answer. And that is, which two variables might be mostly unique? Look at the question. Which two variables might be mostly unique and why? All of these questions are just hinging on the uniqueness section of the table. Which two variables might be mostly unique and why? And why? Who can tell us mostly unique and why? And of course, the way you order them is also very important. Letitia, you're giving an answer which is not correct, unfortunately. So come back again, think through without doing lottery. Which two variables might be mostly unique? Remember, mostly unique. Unique. Grace, your answer is correct. It's variable 5 and 6. Okay. And the answer is because these variable 5 and 6, they are the ones with the greatest, in order, the greatest uniqueness. Variable 5 has uniqueness of 76. Variable 6 has uniqueness of 47%. Okay. So why? Because as you can see, variable 5 has the highest uniqueness value, followed by variable 6. So it is just a way to trick you. So what it means is that 76% of the variability in variable 5 and then 47% of the variation in variable 6 are not being shared with the other variables in the overall factor analysis model. In the overall factor analysis. How you interpret that, how you justify that is very, very important. Okay. How you justify that is very important. So you can see just on the uniqueness alone, we've had so many questions. Now look at the next part. Steven's still there. The question is that these variables, are they relevant? These variables, variable 5 and variable 6, are they relevant? Why? Who can tell us the answer? Are they relevant? This one is a yes or no. Are they relevant and why? Variable 5 and 6, are they relevant? The answer is no. Okay. And the question is why? Well, it's obvious. It's obvious because they have the highest uniqueness and then the lowest communality. That's why they are not relevant. Okay. Now let's go to the next question. Now we are moving to a different section of the factor analysis model. Okay. And that is the factor loadings. So look at the question, which factors or which variable seems to load well on factor 1 and on factor 2? Which variable seems to load well on factor 1 and factor 2? That's a question. Under loadings here. Which variable, and that's a question, which variable seems to load well on factor 1? Let's deal with that first. And then on factor 2, let's deal with that second. Which variable seems to load well on factor 1? Okay. And you see, I said variable or variables. So you got to relatively tell me those variables that load well on factor 1 and those variables that load well on factor 2. It's very important. Now let's go to let's look at the results. No, so let's take variable 1. Does it load well on factor 1 or on factor 2? That one is obvious. It loads well on which factor? That one is too obvious. In fact, I won't look at that. It loads well on factor 1. Okay, you can see. Now let's go to variable 2. Which one factor does it load well on? Okay, variable 2. Which factor? It loads well on factor 2. Okay, you can see it. Now this is where it gets trickier. Variable 3. Okay, which factor does it load well on? I think this one, if you are smart enough, you get it. It loads well on factor 1. That is true. It loads well on factor 1. What about variable 4? Which factor does it load well on? Variable 4. It loads well on factor 1. That's true. Now, variable 5. Which factor does it load well on? It loads well on factor 2. There's no doubt about it. Because you can see that a 0.44 is bigger than 0.22 in absolute terms. And then finally, variable 6 also loads well on factor 2. You are all correct. I mean, all of you are blasting the answers beautifully. So this is the one of the questions that you will get, when it comes to. So in short, variable 1, 3, and 4, they define factor 1. Okay. And this was what you normally have to find a suitable name for. Okay. If you have the storyline in your mind, you have to find a suitable name for. And you remember that we decided to call it service quality. Service quality, because we knew that these were more focused on the service of the restaurant. This was about a restaurant. And then we also established that variable 2, 5, and 6, they load well on factor 2. And the name for that was what? You can remember. We said that the name for that was what? Let me see whether somebody will remember it. Variable 2, 5, and 6. We said that the name for that was what? This one was on service quality, and that one was on food quality. Very good. Very good. Kennedy, that was a good answer. Okay. So that one was food quality. Okay. Now let's go to the latter part of the factor analysis model. And that is, you can see the proportion of variance, the cumulative proportion of variance, and then the loadings. Okay, the loadings. Okay, so I have a question here that would be one of the common questions we ask. What percent of the total variance does factor 2 account for? What percent of the total variance does factor 2 account for? Okay, Derek has just given the answer so quickly. What percent of the total variance does factor 2 account for? What percent of the total variance does factor 2 account for? And you can see, when you look at it very carefully, it is 76%. The word total variance is different from the variance. Okay, total variance was different from the variance. So what percent of the total variance that factor 2 account for? That is different from the variance. So total variance means cumulative. Get a point. Total, so that was excellent, 76. Total variance is cumulative. And so we are talking about the cumulative area. Okay, now let me ask you, what percent of the variance does factor 1 account for? What percent of the variance does factor 1 account for? This one is easy, 46%. I think you're all getting that, okay? Every single person is getting that correctly. 46% of the variance is accounted for by factor 1. So those are some of the questions you are just asked, okay? Now, let me show you the next question, which is an important question. The next question is, does the p-value suggest that 2 factors are sufficient justify it? Does the p-value suggest that two factors are sufficient? And anytime you ask a question on the p-value, okay, you asked, write a null and alternative hypothesis. Write a null and alternative hypothesis. So does the p-value suggest that two factors are enough? Somebody says yes, somebody says yes. Let me show you the p-value. So at the bottom, the last sentence is the p-value. Okay. And then you can see in the story, test of hypothesis that two factors are sufficient. Does the p-value suggest that the two factors are enough? So what will be the null hypothesis? The null hypothesis will be that two factors are enough. Okay. That will be the null hypothesis. So please note, okay, we'll talk about the null hypothesis. The null hypothesis will say that two factors, okay, two factors are enough. And then the alternative hypothesis will say what? All of these have carried marks. The alternative hypothesis, is somebody has gone to write the null hypothesis, yes, no. The null hypothesis actually said two factors are enough. The alternative hypothesis will say that two factors, alternative hypothesis, will say that two factors are not enough. Two factors are not enough. Okay. So once you're able to now execute that null and alternative hypothesis, the next thing you want to do is to answer the question. Now the p-value is 3%, which is less than 5%, isn't it? The p-value is 3%, which is less than 5%. So when you have a p-value of 3%, which we know is less than 5%, what is the conclusion? And it is always the case. Whenever the p-value is less than the alpha, whenever the p-value is less than the alpha, as in our case, we always reject the null hypothesis. And the null hypothesis says that two factors are enough. We are rejecting the null hypothesis, and in this case, concluding that two factors are not, you are concluding that the two factors are not enough. Okay. So you reject the null hypothesis, you conclude. So in this context, we are going to make a conclusion. Let me show you how you write it. Okay. We're going to make a conclusion. The conclusion is that the two-factor model does not fit the data perfectly. Now, this is quite a bit strange because PCA, that's what we were told. So, but then of course, statistically speaking, it was close. But, you know, statistically speaking, it doesn't work the way we want. Boachi, do you have a question?
Yes, Doc. Yes,
Right.
Doc. Yes, please. I want to know if the conclusion is based on how you frame your null hypothesis, because I might also frame a null hypothesis that says that it's not sufficient. Then when the p-value is less than the 0.05, I reject it to make it sufficient, taking the alternative hypothesis. So I want to know if it based on how you frame your null hypothesis.
Null hypothesis is always framed in an equality angle, not in an inequality situation. If you remember when we're doing two sample hypothesis, three sample hypothesis in ANOVA and all of that, you hypothesize in a positive situation. So your null hypothesis says that, okay, anything, the null hypothesis must have some level of equality in it. This is one of the things we learned in undergrad, that the null hypothesis must have some level of equality in it. So if you look at this statement, which of them will have some level of equality in it, and which of them will have some level of inequality? Okay. So two factors are enough. That word, when you're writing it, okay, you bring an equality sign. The word "are" is an equality. The word "not" is an inequality. Okay. And the null hypothesis is always formulated in an equality fashion. And so it's not about how you formulate the null hypothesis. We know how the null hypothesis must be formulated. So when you are having something like even situations of inequalities, okay, even situations of inequality, where you have greater than or equal to, you will choose the greater than or equal to than the greater than. The greater than or equal to will be the null hypothesis because it has some level of equality attached to it. Okay. Yes. So it's not about how you formulate it at all. It is what it is. And in this case, you reject the null hypothesis and conclude that the two-factor model doesn't fit the data. That's it, finish. Now, if it is a practical work, what it means is that you have to try a three-factor model. So in other words, where you specify, let me see whether I can get it. Where is that? Where you specify, let me see whether I can see that for you. No. Because in one other example, I saw that for you. Okay, so it's not here. So where you specify the factor, I want to go back to that for you because it will help you to appreciate. In a practical situation, you know how we started this whole thing and formulated the equations in R, okay? We selected factors to be what, 2. So at this stage, you got to go back, if you're doing a practical work, and go and try 3. Go and try, let's do that. Let's do that here. Okay, let me just, since we have the R here, let's do that. It may or may not work, but then at least you want to be able to, but in this context, it doesn't. So here we chose 2. Let's change the factor analysis, the factors to 3. Because the thing about factor analysis is that you got to assume that you already know the factors. Okay. So let's change it to 3 and run the whole thing again. Now let's see the results. Now, first of all, you will notice that the variables, the uniqueness have changed. Now we have 3 factors and all of that, okay? Now, the degrees of freedom for the model is 0, and the fit was blah, 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 blah. That's that somebody will say, that is interesting, okay? That is interesting. Let me compare that with the first one. That is interesting. Let me do one factor and see. You see one factor. One factor tells you that, okay, p-value is what? Is 2.4%. Okay. So the likelihood is that 3 factors are enough. That is what it means. Okay. It's possible that 3 factors here are enough than 2 factors. It's possible. It's possible. Okay. The degrees of freedom for the model, okay, is 0. So the reason is because these variables, the variables are small. Okay. The variables are small. Okay. And so splitting these 6 variables into 3 is the best. But again, the samples variables are small. Okay. And so it presupposes that 3 factors may be ideal than 2 factors. And you can see that in that case, variable 1 will load well on factor 1, variable 3 will load on factor 1, and variable 4 will load on factor 1. Variable 2 will load on factor 6. Sorry, variable 6 will load on factor 2. Okay. And variable 3 will load on factor, variable 5 will load on factor 3. Okay. 5 will load on 3, 6 will load on 2. And variable 2 will load on 3 as well. So 5 and 2 go to 3. 5 and 2 go to 3. Only 6 will stand on its own. Okay. 6 will stand on its own. And then the other 3 will load on factor 1. That is what it means for a 3-factor model. So that is how you attack it. basically. That is in a practical situation. Okay. But for this exam situation, in this context, based on the p-value, variable, what do you call it? Two-factor analysis do not technically work for it. Okay. So a final note on rotation. Okay. Any of the several methods in factor analysis by which the researcher attempts to relate the calculated factor to the theoretical entities is known as rotation. Like I said, there's a lot of work on rotation, and I don't want to bore you so much with that. Okay. All right. There are several things when we talk about orthogonal and unique rotations, and several work that has been done on rotation. You can read these things on your own. And sometimes researchers even get bothered with when it comes to rotation, so they get confused. Having said that, that brings us to the end of the factor analysis model. I have an exam question, for example, that I set a couple of years ago that you can look at. And this is it. This was in 2014. Opele. That was a starting point of the question. A multivariate research student in UGBS, when undertaking a survey, asked 10 questions. So they had question 1, question 2, question 3. They represented the variables of interest based on a Likert scale. These are the questions. So question 1, okay, had a result of 3, blah, blah, based on what was asked. So several questions on a Likert scale measurement, okay, from 68 lectures. For instance, one question, which is question 2, said that I would like to teach in Ghana than in the UK. That was question 2. So when you go down here, question 2, I would like to teach in Ghana than in the UK. The first person said 2. The second person gave 7. The next person. Now, these numbers, okay, will indicate their value response. Now, what do they mean? Well, most of the 10 questions have ordinal answers, ranging from 0 to 7. In other words, once the person writes 0, I strongly disagree, which means that I will not want to teach in, what do you call it? I will not want to teach in Ghana. Okay. Because the question was, I would like to teach in Ghana than in the UK. Strongly disagree. And then you have 1, which is disagree. 2, somehow disagree. So if you look at this question, okay, the first person chose somehow disagree. That is the first person. He chose somehow disagree. The second person chose 7, which means that he's going to really, really agree. Okay, the next person chose 4. And look at the 4 means neutral. In other words, I'm neutral between teaching in Ghana or teaching in the UK. Anyway, so these were some of the answers that were given. Okay. For example, and then we gave an example, the first person had no opinion. Now look at that. Okay. The first person had no opinion on question 1. Okay. Somehow disagrees with question 2. No opinion on question 1 is 3. He chose 3. Okay. And when you look at the interpretation for number 3 says no opinion. Okay. Somehow that person disagrees with question 2. Somehow agrees with question 5. Agrees with, and on and on and on. Anyway, the purpose of this project is to know whether the correlations among the variables can be accounted for in terms of comparatively few latent principal components. Okay, so the principal component analysis can be performed. The correlation matrix, other tabular results and graphs, blah, 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 in R are all shown below. Use them to answer the question. So you run the whole thing, okay, and then we got this correlation matrix. This was it, across the individual variables. Question number 1. Using the rule of thumb in PCA, which variables appear to be strongly correlated with question 2, with Q4, Q5, Q9? Then from the matrix, is there a basis for PCA? Justify. What is the percentage of variability accounted for by the first principal component? Correct to 2 decimal places. Interpret the second principal component. Interpret the cumulative proportion of variance accounted for by the second principal component. Determine the eigenvalues of the first 4 principal components. And then the results of the PCA are given. Based on that, what linear combination of the original variables account for the fourth and the largest variance? What is the equation of the eighth principal component? Using appropriate table. Okay, and that was the question that was asked. Using appropriate table, how many principal components are extractable? Justify using two approaches. So you have to determine at what point of component does the elbow effect occur? Use the scree plot. Do you think we can proceed to do factor analysis? Why or why not? Okay. So this was a scree plot that was used and all of that. And then you have the biplot here. And of course, in this context, I went ahead and then did a biplot. So after the biplot, questions are using the biplot and other previous analysis, which variables project onto which principal component. Compute the communalities for questions 1, 7, and 9, and determine which one of them is the most informative and why. Which variable is the least relevant and why. And then the factor analysis are given here. Interpret a communality for question 6. Which variables load very well on factors 1 and 2? What percentage of the total variability does factor 2 account for? Does the p-value suggest that 2 factors are sufficient? Justify. Write the first factor model. Okay. The first factor model. So, okay, and then of course there are several other questions that will come on there. So what I've just done is to give you a sneak peek of how the factor analysis model actually works.